Okay, recording should hopefully work. Yes. And now I try to share my screen. Is the screen there? Now let's hope it's stable. And you can see the smiley. Okay, good. That's a good starting point. Fantastic. And I just stepped on a Lego piece, and this is painful. Right. So, and you can see the screen moving. Yes. Good. Because Daria said, oh no. Okay, so what happens if we have pH equals pKa minus log, and we have the same concentration of the acid and the base? And Aidan, please mute. Thank you. So what happens if we've got the same concentration of acid and base? They cancel out. They give log 1. Log 1 is 0. So in this case, we have pH equals pKa. That means if the pH is the same as the pKa, we need equal amount of acid and base. In our situation, our pH is 6.5 and the pKa is 7.5. So let's calculate the ratio of acid to base. pH equals pKa minus log of acid to base. Okay, so we are really interested in the ratio of acid to base. What is the acid to base ratio in this case? Is it again frozen? Holy cow, what's going on? Is team having a bad day? Okay, good. So we need to figure out what is the acid to base ratio. So what we do is we just simply rearrange this equation. We get everything with log to that side. pH goes to that side. And we get log of acid to base equals pKa minus pH. Okay, so I put the log to the left-hand side and brought the pH to the right-hand side. So what do I get? Log acid over pH equals 7.5 minus 6.5, and that is 1. So as I said, I add both plus log acid over base. So I bring the log to that side. So I get pH plus log acid over base equals pKa. And then I subtract from both sides pH, and I get log A over B equals pKa. So we have log acid over base equals 1. But I don't want log acid over base. What do I do in order to get rid of log? How do I remove the log? What's the operation? Absolutely. I take both sides 10 to the power of. So I've got 10 to the power of log acid over base equals 10 to the power of 1. 10 and log 10 cancels out. So I've got acid, concentration of acid over base equals 10 to the power of 1, and that gives me 10. Yeah. So I know that the ratio of acid to base must be 10. Some people also write that as 10 over 1, which basically means you need 10 parts of acid plus 1 part of base. That's the same thing. Or I can just simply write it as 10. I don't have to do the one thing. Does that make sense? That is my ratio. And if I have this ratio, acid over base, I have a pH that is 1 unit smaller than the pKa. So now we have one equation with two unknowns in it, which we can't solve. But we have more information, because up here we said that our total capacity of the buffer should be 220 millimole per liter. And we want 100 millimole or 100 milliliter of the buffer. Now, what does that actually mean? It means that the amount of acid plus base, that gives me the total capacity. So we said we have 220 millimole per liter, and we want to have 100 milliliter of the buffer. So how many millimoles do we need? How many millimoles is the capacity? How many millimoles? Now that's not terribly difficult to calculate. We know how we can calculate that. We say millimoles, and I use dimensional analysis. Do we have millimole somewhere? Yes, we've got it here. So we've got 220 millimole per liter. Now the millimole is good, but we have to multiply it so that the liters cancel out. We can do that with our milliliters here. Times 10 to the minus 3 liter here. That's our 100 milliliter. And if we do that, we get, what do we get? We get 22 millimole. Okay? So that's basically the second step. We calculate from the capacity how many millimole of acid plus base equals 22 millimole. That is what we need. And we know that acid divided by base equals 10. That is what we just calculated here. So now we've got two equations. We can solve it. Two equations, two unknowns, we can solve that. How do we solve that? Well, first of all, we bring this base to that side, and we just simply say acid equals 10 times base. Does it make sense? And can you still see it? Or has it completely bombed out? Am I talking to myself? Ah, okay, good. I was wondering. Okay, so we've got acid equals 10 times base. And now what we can do is we just simply write in this equation here, instead of acid, we write 10 times base. So we write 10 times base plus base equals 22 millimole. Yeah. Yeah, we need 10 times more acid than we have base. Ah. John gets it right. So what we can do is we can just simply factor out, because why do we have two base? Well, I just substituted this acid here with what I calculated here. Absolutely, it's from the substitution. So 10 times base plus base, I can factor out base, which is 10 plus 1 equals 22 millimole. Or base times 11 equals 22 millimole. Or base equals, if I divide it by 11, is 22 over 11 millimole equals 2 millimole. So base is 2 millimole. So what is acid? Well, we can do that very easily. We can either do it here. We said acid equals 10 times base. So is 10 times 2 millimole is 20 millimole. Okay, so we have acid equals 20 millimole, base equals 2 millimole. Okay, together they give us 22 millimole, and that is what we wanted. That was our capacity, 20 plus 2. And the other equation was, we looked at the ratio, and that should give us 10. So we've got 20 divided by 2, and that gives us the ratio equals 10. So we need 20 millimole of acid and 2 millimole of base. Does that make sense, this calculation? Obviously, you will need to do quite a bit for practice purposes. And again, on my practice calculation website, there is exactly how you do this step by step. And as I said, I've prepared a little sort of document for you, which I will send out to you with videos where you can go through that step by step by step. This question is illegal. Oh, no, no, no. This is a very, very common question in any kind of assessment and exam. Because it's really easy and simple. And it's easy. You really have a sort of, you follow a procedure. Now, we need 20 millimole and 2 millimole respectively. So what is that in grams? And we said the acid is 123 grams per mole and the base is 143 grams per mole. Let's see if I can remember that. So acid has a molecular mass of 123 gram per mole, and the base has 143 gram per mole. Absolutely right, John. So we've got the molecular mass, and now we want to convert the millimoles into grams, and that's not terribly difficult. So for the acid, we say we are looking for grams. We have 123 gram per mole. That's our molecular mass. So the grams are right. We need to get rid of the mole. Do we have mole anywhere? Yes, we have times 20 times 10 to the minus 3 mole. That's our 20 millimole that we've calculated for the acid. And what happens to the moles? They cancel out. So here we get 20 times 1, 2, 3. That gives 2, 4, 6. So that would give us 2.46 gram of acid. And I got that right. So we need 2.46 gram of acid. And we do the same thing for the base. So gram, we have 143 gram per mole. We want the grams, so that's in the right place. We need to get rid of the moles, so we multiply it with 2 times 10 to the minus 3 mole. And we get, what do we get? No, you need to be careful. You can't divide it by 10 because they've got different molecular masses. If they had the same molecular mass, you could do this trick, but you can't because they've got different molecular masses. Yeah? So you would get 0.286 gram base. Okay? So you have 2.46 gram acid and 0.2 0.86, or in this case, if we do both to two decimal places, 0.29 gram of base. Does that make sense? But what you can do is, if the masses of the acid and the base are reasonably close together, you see that we need 10 times more acid, roughly 10 times more acid than base. And that was totally in line with our prediction from step 1. Remember, step 1, we said we need more acid than base because the pH is smaller than the pKa. And that's actually a very important sort of quality control step for us. So we are pretty confident that with our calculation, we didn't make too much of a boo-boo. Now, what would happen? And I want you to be really comfortable with this kind of calculation. So that's why I'm going to send out later what this calculation did, the tutorial and videos about that, so that you can really practice that. And I cannot emphasize how important it is for you to practice these calculations, because in the second year, you absolutely need to nail that topic. One thing that I want you to also to think about is, let's say we have a buffer. Let's say we have 100 millimole per liter of acid, and we have 100 millimole per liter of base. And we have this together in 100 milliliter, let's say 100 milliliter. We also have a pKa, let's say pKa is 7.0. Can you tell me what the pH of this solution is? What is the pH of this solution? It's 10? 7? Aha. There are different views. 7. Right. So pH equals pKa minus log acid over base. pKa is 7.0. Log acid is 100 millimolar divided by 100 millimolar. That gives us 1. So we've got 7 minus log 1, and that gives us 0. So pH, in this case, pH equals 7. Right? And I've done A over B, acid over base. And I've got the negative here. Now, what happens if I dilute this buffer? So if I have these 100 milliliter and I add these 100 milliliter to 900 milliliter of water. What's my total volume then? I get 1 liter, absolutely right. So I diluted the acid and the base. I diluted them by factor 10. So what happens to the pH? So instead of 100 millimolar of the acid, if I dilute it by factor 10, I've got a 10 millimolar solution, right? And the same, of course, because acid and base are together, happens to the base. I got a 10 millimolar solution. So I just simply dilute the buffer by factor 10. What is the new pH? What is the new pH of the diluted buffer? What do you think? Reynolds says it's still 7. Why? You're absolutely right. pKa equals log of acid over base. So now I've got 10 millimolar acid and 10 millimolar base. But that still gives me 1. Sorry, that's a minus. That still gives me 1. So we still have pH of the new buffer, of the diluted buffer, is still pKa. So if I dilute a buffer, the pH won't change. The buffer keeps the pH the same, even if you dilute it. Absolutely right. Totally nailed it. So you can dilute a buffer and it will still stay the same. The capacity of the buffer changes, the overall capacity of the buffer changes, but the pH will still stay the same. So now you know how you calculate a pH, how you calculate a buffer, and how this buffer keeps the pH relatively constant. So now you know everything about buffers. And what we are going to do tomorrow is we are looking at an application of buffers. We turn the whole thing upside down, as my friends in Scotland would say. We put that on the head and we will calculate, for example, how much of a protein is charged when we have a given pH. So watch the space for tomorrow and watch your emails. I will send out something later today with some more information. If you don't have any questions, thank you very much for watching, and I apologize for the issues that team has caused. See you later. Be good. Don't do anything I wouldn't do. And remember, life is good.